So my name is Daizhong Liu. I was a postdoc at MPE while I was participating in AtLAST Phase 1, and now I moved to Purple Mountain Observatory in China as a researcher. But I still keep interest in AtLAST because it's really a very unique 50-meter single-dish telescope, and it will really tell us many things different about gas and dust in nearby galaxies. So these are also based on a group of us very good works by, for example, Emily Santosh, Caroline Bott, and all of the people in our working group. So thanks to all of them. And in our nearby galaxy science cases, we actually divide the science case into four topics. The first one is about the Magellanic Clouds, which are our very close neighborhoods. We can, however, there are still a missing knowledge about some part of the gas and dust in Magellanic Clouds. Here I quote it as invisible gas and dust because it was very hard to probe by ALMA because of the missing flux, and also was difficult to probe by smaller single dish like Herschel or some other telescope because of the angular resolution and the sensitivity. And the second part is about the magnetic fields in nearby galaxies. We probably also hear a lot about the magnetic field in molecular clouds in our own galaxy, but does do these magnetic fields change within different external galaxies? That could still be a very big question, especially in starbursty galaxies that have much more intensive star formation than our Milky Way. The third part is about chemistry and physics of star-forming clouds and regions in nearby galaxies. And the fourth part is about galaxy population and environment in local or even extending to nearby and relatively low redshift universe. So starting from the first one about our neighborhoods, we know that our universe have lots of galaxies and the Milky Way is one of them. And this is the local group. This picture shows about 100 megaparsec box. Well, our neighborhoods are all there. And if we, there are actually a lot of matters, including dark matter and the bionic matter. However, only 1% of all this matter in the universe are inside galaxies. Even though this is a low fraction, we still know very little about all how this matters, like gas and dust and stars, distribute or evolve within galaxies. So we can say that we know little about the local universe still. And if we zoom in to like 5 megaparsec box, we can see our very close neighborhoods, like in the northern hemisphere, the Andromeda, and in the southern hemisphere, the Magellanic Clouds, including the large Magellanic Clouds and the small Magellanic Clouds here, if you can see my cursor. And if we further zoom in, we can see that we actually have a connection with the Magellanic Clouds. So this is a Magellanic stream that connects from large Magellanic Clouds to small Magellanic Clouds with very diffuse emission. These are probably radio. They can probe by the very low angular resolution radio studies and also X-ray. But in terms of cold gas and dust, we still know very little. So why ALMA is inefficient in probing this kind of invisible gas and dust? Because of the nature of interferometer, ALMA cannot see extended large-scale structures, but the interstellar medium is large-scale by nature. And while Herschel or other small single-dish telescopes cannot fulfill our science goal to probe this cold invisible gas and dust because of the surface brightness of this relatively diffuse and faint emission could be far unable to be detected by this small single dish telescope. So this picture is taken from the fans work, Leroy 2021, showing that the left panel is the total emission from the map, And the middle panel shows the convo 7-meter array from ALMA, which have a slightly better sensitivity to extended emission, but still it misses a large fraction of these fluxes, which can only be seen by a single dish. So ALMA have the total power array that can help correcting this missing flux, but it's still using 12-meter antenna, which is inefficient in the sensitivity. Compared to the Herschel small single dish, the angular resolution is really not good. So to probe our beautiful Magellanic Clouds neighborhoods, this is a very beautiful picture, and we can only the current telescope like a Nanjing small millimeter telescope can only observe very clumpy CO distribution as shown in these green contours. The background is the even lower resolution H1 observations with an angular resolution of about 2 arcminute. And the CO emission is distributed uh, scarcely and look very clumpy. Whether there are CO emission that is more extended and at a very low surface brightness is still a question. So we really need a 15-meter single dish like AtLAST. So with AtLAST, we will answer several important questions like how much molecular gas is there, especially regarding to the CO dark gas and the gas to dust ratio, and how much dust is there that we were not seeing with ALMA or smaller single dish telescope. There is a millimeter dust excess problem that is extensively discussed in the literature, like Caroline Bott 2010 paper and several others, which are still not solved yet. And technically, if we want to resolve typical GMC giant molecular clouds in Magellanic Clouds, it will require an angular resolution of better than 4 arcsecond. And if we really want to map the large area of Magellanic Clouds, which are several degrees by several degrees, with ALMA very small field of view, it will need 200,000 individual field of views, which means also a very unrealistic observing time with ALMA. So this figure shows the part of the LMC, and in the future, if Roman flies, Roman will have a very much larger field of view even than the JWST, as shown in these irregular distributed rectangles. And if we have an AtLAST, which will have a 1 square degree field of view as shown in this double line square, then only AtLAST can match the field of view of Roman. Therefore, to study our neighborhood's Magellanic Clouds as wide as possible in multi-wavelengths. The second part is about extragalactic magnetic fields. So Sophia telescope on the plan uh, was extremely powerful in studying the high frequency dust emission with polarization. And this figure is taken from Lopez Rodriguez 2021, which shows very beautiful magnetic fields in NGC 1097. And the difference between yellow and the white lines are that white lines represent radial magnetic fields and the yellow lines represent fine-infrared dust grain magnetic fields. Radial might be affected by uh, Faraday rotation problem, whereas dust grains are mostly the thermopolarized emission. They show some misalignment in some regions, which indicates something interesting, especially this in the southern part where we can even see a little bit the orthogonal distribution. So these are really quite intriguing questions. In another case, well, this is actually a not a spiral galaxy, but a merging galaxy, the antennae galaxy. And this also shows very some part of it show ordered magnetic fields, whereas some other parts shows really misaligned distribution. How does this work? What's the nature of this distribution of these magnetic fields? We clearly need something that is more higher angular resolution and also wider distribution. So again, AtLAST will play an important role here. With Sophia, which has already stopped observation and decommissioned, there's no very good instrument that can probe a large number of nearby galaxies for their magnetic fields. So we still need at last 50 meter to resolve these giant star-forming regions with a few second angle resolution and image their polarized thermal dust with very high sensitivity. The third part is about physics and chemistry of star-forming regions in nearby galaxies. We might know that galactic studies will also focus on a lot about spectral line scans. So to have a very wide bandwidth and detecting hundreds or even thousands of spectral lines. This is probably similar, but in extragalactic studies, we will cover a lot more different galactic environments. For example, this galaxy is NGC 253, which is the nearest extremely starbursting nuclear. Uh, there is an ALMA large program called Archemy, which observes a very wide spectra at this nuclear within its central 1 kiloparsec. So this covers ALMA band 3 to even band 6 and 7 with hundreds of spectral lines detected. NGC 253 nuclear environment is not only very starbursty but also have multiple phases of the ISM, including very extended outflow emission and all these nuclear starburst rings or molecular outflows and with different density and temperature. So by observing this very wide band spectra, we will not only study the uh, density and temperature of the gas, but also the chemistry. So the uh, for for the upper panel, it shows the full spectrum of NGC 253 from ALMA Academy Large Program. At the bottom left, we can see the CO excitation ladder. Well, the x-axis represents the rotational transition level, and the y-axis represents relatively CO line strength. For the highly excited high transition CO lines like 6, 7, they will be effectively excited when the gas density is very high, like in the dense clumps. And this temperature diagram also shows that with a higher temperature of the gas, the excitation will move at a higher transition peak. And the bottom right figure shows that a a mock galaxy with its uh, important CO and C1 and ionized lines in from millimeter to submillimeter. These highly excited high transition lines are only at high frequencies. Therefore, for ATLAS, we not only need millimeter like 3 millimeter to 1 millimeter, but also this even higher frequency bands to really recover the excitation of this gas. And about the chemistry, it is also very important. From a chemist NGC253 spectra, we can see a lot of very interesting molecular lines that are detected, like the ethanol, methanol, xenon radicals, and even some indication of the prebiotic molecules. These are quite important for our understanding of this chemistry in the very dense or even very starbursty environments. So with at last in our white paper, so we imagined like we can do a
15
very
minutes.
cool, yes. So we can do a very ambitious study to survey like nearly 100 nearby galaxies, and we can recover like 100,000 star-forming regions and clouds. not only like ALMA, for ALMA, if we it's a survey with ALMA like the fence survey, they can only survey the CO2 to 1 line because ALMA is very inefficient in mapping the lines. But with ATLAST, we will not only recover one CO line, but also multiple CO lines and even multiple uh, more interesting other molecular species. If we imagine a heterodyne receiver with multi-beam multiplex multiplexity like this with a heterodyne with 900 beams, it will really give us a lot of efficiency in recovering all the lines. Therefore, do our large sample statistics. Finally, if we focus uh, on the local universe that is a little bit more extended out to redshift zero point 0.1 or about 200 megaparsec, then we can really study 75,000 of galaxies in our local or nearby universe. This is related to the use of large format imaging spectrometer or something that is related to connecting to the high redshift universe. Well, while we can probably only focus on one CO line which traces the molecular gas, but we can recover a lot of galaxies. So the plot shows the predicted number of CO detections with a 1 square degree field of view, and the right panel shows the existing sample from previous, for example, ARAM 30-meter or ALMA large program, and there are only about a few hundred. But even with 30 minutes, we can compare to the detection of several hundred hours from previous telescopes. So this is a truly submillimeter Sloan digital sky survey in the nearby universe. And this shows that the previous CO detections and the very wide area that we can do this kind of study. And we can also probe the different environments, for example, how molecular or atomic gas like C1 gas are stripped in different environments. So these all rely on a very large telescope like ATLAST 50 meter. And this is the summary. ATLAST will enable groundbreaking knowledge on the invisible gas and dust in Magellanic Clouds to tell us a lot more story about magnetic fields by expanding the sample from like 10-ish galaxies to 100 external galaxies and really tell us about the chemistry and physics of a large number of star-forming clouds and regions, and finally galaxy population and environment in the nearby universe. So the right panel, right figure shows the MacBoost summary paper about ATLAS science, which summarized into three key science topics. Where are all the baryons? How do structures interact with the environment? And the time domain submillimeter physics. Here we can cover the first two key questions. So it's basically a very ambitious and exciting program for AtLAST. Yeah, that's basically my presentation. Let me know if you have any question or welcome to discuss. Yeah, thank you.